Okay, lesson 24, electromagnetic waves. All right, so in this one, what was going on? So we had Michael Faraday was doing everything we did in the last lessons, right? They were learning all about how current through a wire could create a magnetic field. They were also discovering that, moving a wire, like accelerating a wire or moving a wire in a constant magnetic field would induce a current through there. So this were the things that were going on. And Faraday had actually theorized that they must be connected, that magnetic fields and electric fields, there must be some sort of connection between those things, that they're related in some way. But it wasn't until a guy named James Clerk Maxwell, who is, to tell you the truth, he's like probably one of the most important theoretical physicists of all time, which is funny because like his name isn't that well known, right, to the average person, really is in physics. But what he was like a brilliant mathematician, and that was something that Faraday, he was good at math, obviously everybody in this field was, but he wasn't at the same kind of level that Maxwell was, right? And it was that ability to use the math is what was needed to make the next jump here, to figure out what was electromagnetic waves, right? So let's go here. So the principles of electromagnetism so far, this is all stuff that we did like lesson 1921. So the first part was that a constant electric current in a conductor induces a uniform constant magnetic field that circles the conductor. So what that could be. No, it's not gonna let me do it with my pen either. Okay, I'll have to fix that later. Anyway, so what that would be, right? So constant electric currents, that'd be in a wire. That's where you get that like magnetic field wrapping around it, right? So that's what they're saying. You get a current going through a wire, you end up getting a magnetic field. Okay. And then the other part here, so from lesson 22 to lesson 3, was when a conductor moves through a perpendicular magnetic field, a uniform constant current is induced in the conductor. So what that means is that you start off with a magnetic field, and then you have a conductor that's moving through the magnetic field. It pushes a current through the wire, right? So those are like two sides of the same coin, right? That's kind of, it's going back and forth between those. And we did those in the last lesson with the motor effect and the generator effect, right? And I talked about how those are just the flip of the other. So what Maxwell started to predict was that, well, we've been using conductors for all of this, right? Like a piece of wire to have a current current induced through it. Well, he was wondering if that could happen with an insulator as well. And then actually he theorized that actually this could happen in any object. It wouldn't have to be a conductor that's pushing the electrons through or the current through. It could be any object, and actually even in empty space. And that was his big insight here. So he changed our laws above just slightly. And he said a changing electric field in space will generate a changing magnetic field that is perpendicular to the electric field. I'll show you what I mean there in a second. There's a good picture below. And then the second part is a changing magnetic field in space will generate a changing electric field that is perpendicular to the magnetic field. Those things are exactly opposite of each other, aren't they? Right? And that's kind of the key to this whole thing. And I find, well, so here's what he did with this idea. He related this now to electromagnetic waves. They didn't call it this at that time, right? They call it light. But here's what it is, right? So propagation of electromagnetic waves. Here's what's going on. And I remember the first time I learned this, it blew my mind, where I was like, oh, that's what it is. Like it actually just kind of ties it together. So maybe you'll have the same reaction. So here's what light actually is, right? If you look at this picture, well, you see this B, like B1. So what that is that's going to be like a magnetic field circling, right? So, and then this is an electric field circling and yada, yada, yada. So here's where it came from. So you see this thing that says increasing E1. So this arrow going straight up and down, you can picture that as being like a moving charge, right? So if you had like an electron that jumped from like here to here, like it was moving through space. Okay, well, what would happen when that thing was moving? Well, we know what happens. You could use your hand rules. You could use your second hand rule, or sorry, your first hand rule in this case, to figure out which way the magnetic field was going, right? In this case, this would be like your right hand going, your thumb pointing up and your fingers wrapping around this way with your magnetic field. But then what Maxwell said is that if you get a changing magnetic field in space, that induces an electric field in space, right? So this magnetic field will create its own electric field. Okay, well, if you get a changing electric field, which this one is, right? It's going in a circle, so it ends up being a changing electric field, right? It's changing direction all the time. Then that is going to change my magnetic field, or it's going to induce a magnetic field, right? So we get, and then now that we have a magnetic field, right, going this way, well, that's going to induce an electric field, and then that's going to induce a magnetic field, and that's going to induce an electric field, magnetic field. And this is what light is, right? So when something is moving at the speed of light, it's actually just this process of magnetic, electric, magnetic, electric, magnetic, electric, magnetic, electric, right? That's how fast that propagation is happening. That's happening at 3 × 10⁸ meters per second, right? Like very fast, but that's essentially what it is, right? So that is why we call light an electromagnetic wave, because it actually is. It's a magnetic field, an electric field, and a magnetic field, an electric field. Keep it on, like going and going and going, right? So yeah, so that's the idea. This is technically like, this is a great picture, I find, this one to picture what's happening there. But then before I keep going here too, the other part of this is that this thing is self-generating, which means it doesn't need a medium to travel through. So what I mean by that is, like a water wave, well, that needs water to travel through. A sound wave, that needs the air to travel through, like air is the medium. A light wave is self-consistent. It doesn't need anything else. It's creating its own fields, right? That's just a field, a field, a field, a field, a field. So it doesn't need anything to travel through. And that's why electromagnetic radiation can travel through space, right? That's why the light from the sun actually gets to us. So it's a self-generating series that radiates in space. So another way to look at this is with this diagram, right? So this part of the wave, this E, that'd be my electric field, and this B would be my magnetic field. A big theory part of this is that these are always at 90 degrees to each other, right? The electric field and magnetic field are always at 90 degrees to each other. And yeah, so if this thing is propagating through space, like I know this picture is kind of hard to see how it turns from that into this, but if this thing is propagating into through space, then you can picture it as being a sine wave. You guys might not have taken Math 30-1 yet, but this is a sine wave traveling through space, and so is this one, but they're at perpendicular angles to each other. Okay, which this makes sense actually. We talked in other lessons, I forget which one it was now, but the polarization. So that's the other part of this, is that you can see that this light could be polarized, right? It has an orientation. So yeah, hopefully that kind of makes sense and blows your mind like it did mine. Yeah, okay, so Maxwell's prediction. So here was his theory, right? So he came up with this idea, and he was predicting that the primary cause of all electromagnetic waves is an accelerating electric charge. This is going to become a lot more important, especially when we get into quantum mechanics and nuclear physics a little bit later. That what I'm talking about there, the accelerating electric charge, he's talking about this part right here. What starts it, right? And in this case, it was an accelerating, proton or electron or, some sort of something with a charge, right? That's what starts it. So all light that you see all had some sort of charge accelerating as its origin. All light in the universe, which is pretty profound in itself, right? And it has to accelerate though, right? That's one thing too. It can't just be moving at a constant velocity. It has to be like an accelerating charge. Okay. When electric charge is accelerated in periodic motion, the frequency of oscillation of the charge will correspond exactly with the frequency. So what that means is if I had a charge that was oscillating up and down, up and down, up and down, well, the frequency of the light would actually match that, is what they're saying, okay? All electromagnetic waves will travel well, he said this, right? 3, this really big number. And this is what he found, right? Actually, this is actually like its own triumph in itself, is he actually derived this number, right? Which is very close to what we know the speed of light is right now, right? he derived that all mathematically, right? And all from just what he knew about electric fields and magnetic fields and how they interact and how they would propagate. So that's impressive, right? Like when he comes up with a number like this that is so close to what we found to be the speed of light in a lab, right? And he was that close just using math. That means he's on to something, right? Like that's a theory that I think that's pretty that is saying something that's true. But anyway, so he said that all light travels at this, which is slightly off from what we know, and obey the universal wave equation, right? So it's a wave, so it's going to follow this, where you've got the speed of light is equal to the frequency times wavelength. Okay. The oscillating electric and magnetic fields will always be perpendicular to each other. That's a big part of this, right? There's lots of questions that are kind of based on that you guys understand that an electric field and magnetic field are always perpendicular to each other. You should have this picture in mind when you guys are doing this. Okay, what else? The electromagnetic waves should show all phenomena associated with transverse waves. So transverse waves are waves that go up and down, right? They're not a pressure wave. They're like a wave that goes up and down. And all transverse waves, you know, that's everything we've been learning about so far with interference patterns and diffraction and refraction and polarization, right? So if his theory is true, we know light does these things, so it should also do these things as well, right? Electromagnetic waves should produce pressure when they came into contact with the surface. So this was in his theory there, right? We'll talk more about that later on, especially in other when we get into quantum mechanics and stuff. Okay, so now Maxwell came up with this he's a gifted theoretician, right? Like he's good at coming up with the theory of these things, gifted mathematician. But he wasn't a great researcher, right? Like he didn't have the ability to design his own experiments and figure it out, right? So that'll be a common theme actually going forward here, where we've got two different types of scientists. You've got your scientists that are doing the theory behind the stuff, often a lot of times like really heavy with the math. And then you've got your researchers and your experimenters that are great at setting up these different experiments, right? So we had a guy named Hendrik Hertz, right, where he designed this experiment where he said, okay, if this is true, this is what would happen, right? He created this where pretty much he just had high voltage across two wires essentially that would create a spark, right? So a spark would jump from one end to the other here, right? And, you know, just looking at just that picture for a second, if we go back up to this one, right, the spark is kind of like the jumping charge right here, right? So it would create a spark, and they say, okay, this is true, then this is what would happen. It would create a magnetic, then electric, and then magnetic, and then electric, all the way across until it came over here. And if the magnetic field was lined up just right, it should induce a current, right? It should induce a current here. So he said, if we induce a spark over here, it should send like an invisible electromagnetic wave across here. And then that should induce a spark on the other end here on this other coil. And it did. He was able to show that. Yeah. And then the other part here that was significant was he was able to create the spark. But then if he turned this coil at 90-degree angle, right? So he turned that like totally 90 degrees to this, the spark goes away. And the reason why the spark would go away is because it's lined up with the wrong field. Then he would have been lined up with the electric field. He would have been, which he needs to be lined up with the magnetic field to induce a current, not lined up with the electric field to induce a current. So he's kind of showing that if he lines it up one way, that he gets a spark, and lines it up the other way, he doesn't. He's showing that these two fields are in fact perpendicular to each other. So it's more support for Maxwell's picture of a wave.
Reflection with Maxwell.
Let's stay out of this. Okay, so electromagnetic, yeah. So electromagnetic waves are light, right? So this is just like more fundamentally what light actually is. Okay, so you guys have seen this, right? This electromagnetic spectrum. And we're going to go a little bit more into it again, but when we get doing these questions, I want you guys to know there's a few things that you're responsible for memorizing and knowing here. So here's your table, right? So you got wavelengths, you've got your radio waves at one end, you got your gamma rays at the other, and this and visible light is just a small sliver of this whole thing, right? So there's our, you know, red to violet all the way here, right? But it's all electromagnetic radiation, the whole thing. There's really no difference in any of it other than the frequency and the wavelength. They're all traveling at the speed of light, but they just have different oscillations. Okay, so you need to know the various members of the electromagnetic spectrum and their approximate range and frequencies. So you need to know generally with visible light what the range is for red to violet, right? So 700 nanometers to 400 nanometers. You need to generally know that. You also need to generally know that radio waves have this much of a spectrum, and they're on the left here, right? And kind of like where they start and where they end. Okay, it's not going to be a hard, like I'm not going to, like, yeah, mostly it's going to be your light and then generally where these things go, okay? And then the other one, knowing how each type of radiation is produced. So I'm going to show you in a second below a little table that is helpful. And then using the universal wave equation to calculate wavelengths and frequencies, right? So you guys have done a bunch of this already from the other unit. Okay, so different parts of this spectrum and how they're produced. Remember, they're all produced from an accelerating charge. So if we have low frequency AC or radio, like these sorts of ranges, like really far down this way. So what causes those? So oscillations in electric currents containing inductive and capacitive components. So really this is just going to be like electricity, right? So electricity can cause these things. You can literally have, you know, the like current going through a wire is going to cause our you know, different radio waves. One thing to notice too is that radio waves are so long, right? They have such a big gap here where like 10 to the power of 3 for my wavelength. Okay, well that's 1,000, right? That's big. That's like one wavelength would be 1,000 meters or a kilometer, right? So that's huge. And all the way up here where we're at like 10 to the, or like 1, right? This would be like 1 meter, and then 10 to the negative 2. So yeah, we're getting like to the point of like centimeters, right? So anywhere from like a kilometer to a centimeter for our radio waves. Okay, and then microwaves, oscillating currents, you know, in general, I know I said you have to know like how they're produced. You won't need to know like the exact details of all of these like things, but just generally. So now infrared radiation is going to be transitions of outer electrons in atoms and molecules. So I really wish my pen worked. Oh, it does. Started working. Okay. Okay, so it's worth talking about. We're going to talk more about this in other units too, but infrared radiation and visible light, and a bunch of them actually, come from this. So if any of you guys have taken any chemistry, then let's say we just took like, you know, standard hydrogen atom, right? So you've got a proton and you've got an electron orbiting around the outside. And maybe you remember from chemistry that you have these different like orbitals, right? You've got these different energy levels where the electrons can hang out. So what will happen is that you get an electron that's hanging out on a higher energy level for whatever reason. Maybe something bumped into it and gave this electron more energy. So now it's sitting up in a higher level. Well, it sits up there and it's not happy. Then eventually the thing comes falling back down again. Okay, well, when you got that moving charge, right? You got that accelerating charge jumping back down again. Okay, well, there's our wave, right? That's what's going to cause our light wave. And actually that's going to cause all the light that, you know, from to our eyes. That's typically the different colors that we see is happening from this phenomenon. Okay, so that's what it means when it's transitions from outer electrons and molecules, right? It's jumping down from one energy level to another. If that didn't make much sense, don't worry about it. We got like a whole unit on that. So, okay. And then just when you get farther down here, you get X-rays and gamma rays. And these type of things are happening from more like inside the atom itself. So you get, let's say if you've got some nucleus and something from the nucleus, maybe like a neutron ends up like escaping, it like leave. Well, that makes everything on the inside kind of reassemble here, right? They would all reassemble, and it's that accelerating, and there's like huge amounts of force happening there, and like a lot of acceleration of that charge. I guess it wouldn't be the neutron, it'd be the proton reassembling that would cause it. But then what that's going to be what causes that little tiny wave, right? Like a gamma wave or cosmic rays or anything else, right? And these things are tiny, right? So tiny wavelengths, but really high frequency. That's what these numbers are, right? Really high frequency. Okay, so things to help you memorize some of these that you have to. You should remember that light is in the range of 700 nanometers for red to 400 nanometers for violet. That's the range that visible light is in. You should remember Roy G. Biv for your colors for visible light. And then just generally this is what you could remember for the different parts of these, is that TV, starts at 10 to the 8 for frequency, and gamma goes all the way up to 10 to the 20, and they go up in steps of 2. So it's kind of helpful there. So yeah, so you might have to, yeah. So that's going to be what I would look at to kind of memorize if you can. Okay, that's it. No practice problems for this one. We just have the handing assignments, and you'll notice there's not even any math really. I guess there's some limited math, right, with just the simple wave equation. But other than that, that's it.